Okay, this is a quick video to discuss the different approximation or numerical methods we have for approximating integrals. To keep things simple, I'm going to focus to a single subinterval. Looks like a simple function here. This is meant to look like zoomed way in on an interval after you've done more than one cut. We're first going to look at the first level approximations, which are left-hand and right-hand approximations. For a decreasing function, the left hand is always an over approximation. The right hand is always an under approximation. The reverse is true for an increasing function not shown. The next level up will be the trapezoid approximation, which looks something like this. Now graphically, that can be seen as the average of the left and the right. This being the right, this being the left. If I take the difference, which is this box here, and cut it in half geometrically, I get the figure shown here. This is what we call our second level approximation, and is likely the best one you could have used in Calc 1. Notice that it uses an over and under and averages it to figure this out. You're not guaranteed to have over and under approximations, but if you cut n up, make n large enough to make the subinterval small enough, you are likely going to have intervals, or at least the subintervals, which are always increasing or decreasing, or at least all but a very small few. So the question comes, how does the trapezoid rule differ from the midpoint rule, or the midpoint approximation? And from this picture, it's not really clear what the difference is. The trapezoid rule obviously approximates the picture by using a secant line from here to here. A secant line being connecting 2 points along the curve. The question is, how can I visualize the midpoint approximation? Well, turning on a little cheat button here for me. This being the midpoint between the green and the red lines, if I take the line and tilt it, notice I've added a little triangle of area here, but I've subtracted the same triangle there. So moving this dot here does not change the area at all. There's the original midpoint. This is still the same area, and graphically, it's kind of cool to put it right there. Notice that now the red area is simply a trapezoid as well, but it's not the secant line trapezoid, it's the tangent line trapezoid. And in this case, you can hopefully see that the red approximation is better than the green approximation. The question is how much better it is. It ends up being that it's that whole 1 to 2 or 2/3 and 1/3 you should have read about in the textbook. Mainly because we look like a parabola in between, and therefore this being 1/3 and 2/3, you look at the integral of x squared between 0 and 1 or something similar. So then the question is, what's the next level up? We should know this. Let me go ahead and put this back to the, let me leave that there actually. Turn those off and look at the Simpson's approximation. This is if I average the midpoint and the trapezoid rule fittingly. I get that. That's probably hard to see. If I zoom in, I'm simply approximating this interval by a parabola. And in a lot of cases, I get a very good approximation. And in fact, if I look at the situation here, the left had an error of 0.04 negative, right 0.05. Trapezoid is, again, about 10 times as good, as is the midpoint error. But notice, again, the trapezoid error is about twice as big as the midpoint error. But the Simpson's error is negative 0.000013. We're talking 3 orders of magnitude better than left or the right, and 2 orders of magnitude better than trapezoid and trapezoid and midpoint. So this is why the Simpson's rule is definitely superior, because with the same number of cuts, I get a much higher precision. It just requires a little bit of algebra rather than calculation. Any other questions about this, please let me know.